The reason that I'm here is because Amelie called me a little while ago, and I had just seen some discussion on by some of my colleagues from JPL on the crash of the ESA lander at the end of October, and I made the comment that one of the problems is that people don't quite understand how to deal with failures. This might sound a little bit egotistical, but here's the success rate of going to Mars. It took a long time before we got off at 0% success. The first half dozen or so missions all failed, but we've still never crossed the 50% success rate. In fact, it seems that we sort of converge at about 45%. So it just flat out is hard, and our latest crater is shown up there on the upper right, but these images at the bottom are some of those early failures that look sort of similar. So in other words, it's pretty easy to blow it going to Mars. It's very unlikely to get it right. But I've been really lucky. All those green bars, every one of those things worked, and those are the only Mars missions that I've worked on. So, or that my code has predominantly been aboard. Am I lucky or just in the right place? Probably just lucky. If I wasn't at JPL, I never would have worked on any Mars missions. Life is a series of random events that hopefully we're prepared enough to take them when the opportunity happens. But I think that there really are some reasons why the system worked. I don't think we were just lucky. Or at least it wasn't dumb luck. Maybe it was smart luck, but it was still a huge amount of luck. So there's this software. I've done pretty well in software, but I happen to have done pretty well with a large series of companies that I've founded and/or purchased over my lifetime in all sorts of different ways, and as well as doing things like I was a sailing master on that yacht there on the right-hand side. So I've done a whole lot of weird stuff in my life, and through those things, one starts recognizing certain patterns of stuff that works. When you're doing stuff that's hard, it's not only flight software that's hard. There's a lot of other things like businesses that are hard, but venture capitalists that are dealing with one of the hardest parts, starting up companies, are finding higher success rates. But one of the weird things that they're noticing is that if women are running the startup company, the probability of success is about 3 times as high as it is when men are running the startup company. And maybe, so like in a whole lot of the companies that, just to kind of go back one, most of these companies I hired women to run the company, including Westlawn, the woman who actually runs the company. She knows how it works a lot better than I do, and I think that there's a reason for that. Men and women are different species, right? We have half of our genetic code only comes non-disrupted from our father, and it's only the other half that we evolve. And women both halves evolve. So it's kind of why they're better at doing modern things than we are. We're still stuck in 100,000 years ago, and women are evolving better. And one of the things that you really notice is that women talk to each other much more. They communicate a lot more. Figuring out win-win situations is an important aspect of most women communication, where men communication is somebody's going to win. And that's very, very different, and it has a huge impact when you're trying to do things that are hard. We're starting to see that agility works, agile management and so forth, agile development processes, and what's really required about that? It's this, that you need good people that work hard and are very committed, that work as a team, not as a bunch of heroes. And so, like over the last a few decades, the VC area has seen their rewards kind of shift. It used to be that the vast majority of the companies that they started, it was just a complete waste of money. That they pour this money in and nothing came out, but maybe you'd get a Microsoft or a Google or something like that, okay, now you make money. But the vast majority of them, they'd get very, very little value out of what they poured money into. Over the last 15 years or so half of the time of these two graphs, you can see that the amount of value in red there, the amount of value created at no matter how much money that they're throwing into the pot, the amount of value created has gone way up. So even if the company doesn't work, there's probably some assets to get from the collapse. Whereas in the early days, almost nothing came out of the vast majority of efforts. So the point is that this agile management, it works on hard things. It more or less emerged from the software area, because software we work on tougher problems than anybody else ever does, and so we've developed approaches that work, and we've sort of put away the old waterfall approaches that work great if you've already done it before, but software nobody's ever done it before. I mean, if you're changing it, if you're writing it, if you're reusing it, fine. But I mean, if you're creating code, no one's ever done it before. It is TRL level 0. So I mean, it's hard. It's hard. In order to make these things work, these are human endeavors. So some of the aspects on teams are this idea of making sure that everybody knows what they're supposed to be working on, but also what that not everything is of equal importance, and so what you should be trading off, what you can be sacrificing as you chase the really critical thing, and to really focus on stuff that matters, the actual real deliverables instead of the make work items. Like you don't get any credit for going to a meeting, you get a credit for something that works. You don't get credit for a document. You get credit for the system that might perform to that document, but delivering the document really doesn't get you any closer to the solution. So these agile approaches that software people are doing, but most startup companies are following now, that's kind of what it's all about. Focus on value. Get stuff so that it works, and your probability of things working goes up. One of the things, though, that we always deal with is that we have managers whenever we've got a team, and there's been a whole lot of psychological tests on managers and things, and they find out that the vast majority, like 70+% of managers, are really bad at the set of skills that are actually super important for managing. Listening to people, responding to, with like, I understand where you're coming from, right? Those kinds of things. Instead, again, most managers are men, and men want to win, so, these are all part of a win-win attitude instead of a me-win attitude. So again, these are some of the things that are super important in how do you actually succeed? So quite possibly firing the managers and getting people that really can emphasize with everybody on the team and see everybody's viewpoints. Make sure that other people's ideas get recognized as well. These things are very important to actually pulling off very tough problems. And you'll see that out of all the various projects, like here we go. Here's an example. I'll leave the acronyms off. Just to obscure it slightly, to keep the guilty unknown or less known. But anyways, I worked on a fantastic project, and everybody thought it was wonderful, and we all came away from that going, God, aren't we great? Aren't we super? And then another project went on, and some of those managers went to the second project, and the second project was kind of a disaster, probably by any metric, but by most metrics, and certainly compared to Project X, Project Y was a disaster. And one of the things was that the managers that moved over were the managers that did not, that were really bad in this, like most managers. And very quickly they just sit there and go, well, if I can argue my way, or if I can talk louder, things like that. That's not how you actually solve difficult problems. That's how you solve really simple problems, but that's a bad way to solve complicated problems. So making sure that you've got the social rules in place, the value system, so that the right kind of people get in those roles, that people that think about others are better leaders than people that think about themselves. So these are really important. And another really crucial part of the whole process is science, which I call it playing. The idea that you do something in a way that it can be measured and that is possibly competitive. Again, this idea that maybe you've got multiple people that have good ideas on how something ought to work. Let them go and see who wins. Instead of just kind of a priori going, well, this person argued louder in the meeting, so therefore, well, that's a lousy reason. You want to be making good, solid reasons, and they should be based on evidence, on some information, on something that you've done, not talked about, not claimed. So that's sort of a super critical part of it. Now, a lot of you guys know that I start out sailboat racing with my family. I'm the one in the middle up there on the boat in the back, but most of these other people I still know and hang out with today. The red boat in the upper right, that was mine for a decade. And now I'm in this boat design world. Both these boats on the bottom here are designed by my students. This one on the left is, for a long time, it was the biggest privately owned yacht. It's for Barry Diller and Dion von Furstenberg. The one on the left is a really cool, fun little trimaran that the French are really getting into for single-handed racing off the coast there. So what I'm doing now is just kind of getting into, can I bring up people in these other fields in a way that they approach it using agile technology, agile approaches, trying things out. And one of the reasons why it is working in the school, we've got 2.5 times the enrollment as we had a year and a half ago, so it's certainly working. One of them is this recognition that I was fortunate enough to get very early on. Did anybody else, was anybody else in here your very first introduction to numbers and math? Was it a graduate control theory class, or was I the only one? So that is actually how I first learned math, was by going to control theory classes when I was very young. And so I learned the patterns of what equations looked like as being important, rather than 7 equals 3 plus 4, right? That I didn't really know how to add much when I was dealing with derivatives and second derivatives and seeing how those things affect feedback loops. So I've always liked state-oriented systems. And the remarkable thing about state-oriented systems is that even when they're really simple, like this little equation here is about as simple as you can get, the chaos emerges rather fundamentally. So this little graph up there is a graph of this very trivial equation down here at the bottom. And I think that this this exposes sort of a fundamental of testing and how you know when your system works. How come these spacecraft worked? Why have all the Pathfinder architected spacecraft? Why did every one of those things work? Well, part of it is that the testing, rather than being based on a set of explicit tests, I mean, it was those too. The idea of the testing is to discover the performance envelope, sort of the classic test case of do this 5 times, do you get the answer 7 out of it? That's sort of like dealing with that stable portion of this function to the left there, when it's less than about 3. Um, and that yes, you can sit there and show, yes, there we go, it's in there. But in fact, most of the state space that the system is going to run in is chaotic, like the right side. So you just finding something that goes, yes, I have found a path through the code that works, doesn't really tell you very much. The results can be anywhere in that whole volume there of this with various amounts of concentration of values. Some are sparse, some are quite dense. But this is a characteristic of most systems, that in reality there's very few non-chaotic systems, especially when you start when you've got state in there. It's just that simple. We when we learned algebra and that sort of stuff, we sort of learned all these rules about that there is an answer. In general, there is not an answer. There's a huge range of possible answers. And so you've got to run your testing regimen in a way that you are exploring this performance envelope, not just having some test cases that certainly work, but when does it not work? Do you know when it doesn't work? Those are actually the critical things, and much harder to do. Some ways of doing this are doing what hackers do. How do hackers break into systems? They usually just try stuff, just try random numbers, just throw stuff at a web socket and see what happens. See if eventually you get a shell prompt coming back at you. Did you kill the server or not? So you need to incorporate some aspect of that in your testing. On a couple of the lander crashes, the recent one as well as the original Mars Polar Lander one, were both caused by noise that the system just kind of took, well, it's a value, I'm going to believe it. Instead of kind of going, is this really? Instead of looking at what are all the ways that an IMU can lie to you. Lots of ways, right? When you saturate some of the axes, the vector represented by the quaternium that comes out, some of those axes were truncated by the saturation. So the magnitudes are wrong, the directions are wrong. So, but if you start out using that, you're wrong. You have to sit there and be concerned with when are you out of this space? When is it invalid? At what point does your system break? Not just can you show that it does work. That's sort of a really key aspect of it. Now, one of the things that we don't tend to do very often in the space community that the industrial community must, like for example, Etsy, right? Etsy's, you guys familiar with Etsy? Very many of you guys here. It's sort of like Amazon, but it's for where you can buy handmade stuff. And Etsy's internet e-commerce company. It's founded and running out of Brooklyn, New York. And I went in there, and one of the things that kind of amazed me was that on the very first day when a software guy software engineer starts working, the first day they push code to their production system. And the company does lots and lots of updates a day, maybe 100, 300 updates to their production system every single day. Can you imagine us doing that on a space mission? People that have a heart attack. Why do they do that, though? Do they do that just because they want to be dangerous or lousy or have a system that crashes? No, it's exactly the opposite. They recognize that your system is a chaotic system and nobody really knows if it works or not. And so you need to be able to observe the system and see how it's actually working. And what they found is that by being able to push something out to production, but also being able to pull it back out of production or push something else out of production in a moment, that enables them to deal with both bugs in the code or an attack. Because what's the difference? What's the difference between somebody really trying to break your web server and just a code in there that's breaking your web server? I mean, the attack is trying to trigger a bug. I mean, it's the same thing, basically. So in order to deal with the security issues, they run these pattern matching algorithms across their log files to watch for things that shouldn't be happening, like, is the amount of heap space continuously going down. Oops, I bet somebody's got a leak. That shouldn't be happening, right? So watching for some patterns like that, making it super easy to add additional patterns that they're scanning for, so that if they go, oh, well, somebody was sending a whole series of strings added with varying, oh, well, that's somebody's trying to break in. So we'll turn that off. We'll start just rejecting everything coming from that node. Picking up on that sort of thing. How do you do that? Well, if you recognize your system is chaotic, which it is, I don't care what you hope it is. The fact is that it is. Since your system is chaotic and it's not repeatable, then make it so that you can tell, even in the noise, whether or not, what's the signal. Looking for a signal in the noise, looking for patterns in the log files, so that you can tell whether or not it works. Now, this kind of requires, they can push to production on everything that they do, right? They can change their, rev the version of Python or Ruby and Java and everything else that they're using without a problem. Rev away. They don't get stuck. Because everything is set up so that they're watching everything, expecting everything to be chaotic, building into the set of tests that they think are important. Updating the tests is as important as updating the running code. And in that way, they can maintain this system that is very, very stable and has been very resilient from attack. So this can be done, but it sure takes a different mindset. Our historical waterfall approach of, here, write a bunch of code, and now we're going to have a tester that goes against the requirements and makes sure that it does all the requirements and I've got a test that, what's it called, the incompressible test list. I've got a test to show whether or not it does that or not. No, you don't. You don't. That's just not. It's just not true. So why follow practices that are not based in reality? So that's basically my talk. I've been lucky. The stuff has always worked. But I think that the reason that I've been lucky is that the architecture which I've gone, you guys have heard my talks before on the Pathfinder architecture, that architecture is structured to map to an organization of human beings that know what they're doing, that the various people can have expertise, and the software that person writes incorporates that expertise. So the software is a model of the human experts that are behind it. So if Scott is working on some subsystem and he wants to change it, go ahead. I mean, it's based on what you're thinking, and as long as it does what everybody else sees, that's fine. So that separation between interface and implementation was I think a very important part of it. Also, the fact that software mapped to a human. So if, like a fault protection engineer, there was a Stucky to do fault protection. There was some code that person worked with, and there was a mechanized manner to make sure that fault protection engineer was in the loop for when somebody found a suspicious problem in their code. There was a mechanized way to make sure that it was known that this was an issue that had to be dealt with at a more global scope than the subsystem. And that combined with the ability to easily expand the automated test cases, and having some people do the million monkey or infinite monkey test, where you're really figuring out what the performance envelope is, where it works and where it does not work. Those were really the combination that made it work. It was the humans, not the technology. The technology was just as close to the humans as we could make it. And the result was as successful as that group of humans is, which is a pretty good group. So that's it. Anything else? Any questions about this stuff? Yeah. Yes, I'm.
Do you have a microphone?
Oh, do it.
No.
I don't have this one. Where is that? Where's the pass around one? I don't see it. Oh, there it is. It's on the bottom of the.
So I want to draw, if you could go back a few slides.
Mm-hmm.
Not this one, this one.
Managers.
So, I want to, I actually want to focus more on the list of things you put there.
Mm-hmm.
So in the keynote talk, Bob Martin said he was looking at a piece of code, and his reaction to the code was rude, right?
Mm-hmm.
It was a rude response. It was sort of a rude awakening or a rude response to him, right? And so when you're doing software development, right, so sort of what I'm getting from your talk and his talk is that interaction between people is very critical, and that
I agree.
things that impede that interaction are detrimental to success.
Oh, yeah.
So that's my. So I just want to know if you can comment on that.
Yeah, the first time we really used an agile management approach at JPL that I'm aware of was the Pathfinder project, where it really came down to really communicating, each person owning their own stuff and knowing everybody who they're dependent upon and who's dependent upon them, and so getting the individuals to basically work the system engineering issue so that it was a co-located and independently responsible team. We were all up in building 230 on the second floor or third floor or whatever it was, and just physically right there, cut out of the line organization completely. Now, and I think that that ability to have direct communication was super important. Now, you were around in the 90s, and so I'm sure that you were aware of the backlash that those of us on the Mars Pathfinder mission got from line management following that. For example, the vast majority of us got 0 raises the entire time we were working on Pathfinder. It was kind of a goofy thing, but the line felt that they were removed from influence in the project, and as a matter of fact, they were. The division management had no real input in there. Now there was we lied about that. We kind of went to great lengths to try to make up ways that how the line helped us out. But in fact, following Pathfinder, starting with DS1 and the missions thereafter, there was always a very strong insistence that a Pathfinder project would never happen again. That we must do it the institutional way, right? And that reduction in the responsibility of the people in the team and the ability to control communication caused the subsequent missions, which were still successful, to be amazingly more expensive, not a little bit more expensive, tremendously more expensive. And the vehicle that came out the other side had more instruments, but less, fundamentally less autonomy. On Pathfinder, we had time to really do an awful lot of artificial intelligence on the system, so that we had about a dozen high-level goal-oriented commands that we used to do the mission. The command dictionary had about 300 commands in there that were, a lot of which were very low level. We could read and write to every register, that sort of thing. But the ones that were used for the mission were a set of about a dozen high-level goal-oriented commands. On the MER and MSL missions, we never got there. Now, rather than constantly over-delivering like we did on Pathfinder, Sojourner was a very unlikely option. No problem, we had it on there. We got it in there. We got a lot of capability on that vehicle that went way beyond what it had to do. Even its 3-month life, it was only supposed to last for about 4 to 7 days. There was the difference between doing it in an agile way, even though this was before the Agile Manifesto. The concepts of agile predate the Agile Manifesto by decades. But even though we did the first one in an agile way, we certainly did not do either MER or MSL using anything that could be described as agile. It's as anti-agile as you can make it. And I think the results are very clear to see. Much more expensive, much tougher schedule problems. Lots of systems that had to be dropped instead of enhanced. Much more expensive to operate. So there really is, even within that that same organization, same geography, same paycheck, mostly the same human beings. The difference in performance is remarkable. Going to you might remember that one of the last things I worked on was that how can we do missions for 5% the cost, and how many problems came from that proposal. Right, the organizational resistance to that proposal. Yet, when I went to Millennium Space, we were able to do it for 1% the cost, easily. Not a problem. It wasn't like, oh God, we're killing ourselves doing this. Nope, not a problem. So by using agile approaches, by really paying attention to these sorts of human factors, the kinds of humans you have on the team, the kinds of leadership you have, the ways that people communicate, the value, it is important to let more than one person try things instead of just choosing something based on who argues the loudest. All those kinds of issues are really important in startups, in rapidly scaling organizations, in organizations that are trying to go for a very low cost, high value kind of play, which most companies do. Face it, that's sort of why most companies exist, is because they can provide better value. These are hard problems. They're hard like software, and they respond to the same sort of approaches. If it's in fact a very effective approach for software development, it tends to be really effective for running a company where you don't really know who your competition is and what the constraints are, and maybe you've never done it before because it's a startup. It's an innovative, disruptive startup. So there's a lot to be seen and borrowed, and now luckily, since it's not just software people doing agile management, there's getting to be some really good studies on this, on you know, like what kinds of things really make the difference in your team. You know, how do you judge who you want to have on your team? You know, still in the software world, we're such geeks that, you know, that often it's a, here, do this programming you know, example, and let me see that you can write code. You know, of course you can write code. Why would you be here if you couldn't write a code? But that's not what makes a difference on the project. On the project is how well you get along with other people and share ideas and make progress, you know, instead of disrupting everybody else's progress. So.